All right, class, we're going to continue this discussion of functions and graphing, which is where we have been. We're going to talk about graphing transformations and then kind of continue. Uh, I'll probably have a few more questions from the written homework in here. We had, as you guys saw watching the last video, there was at least one of the questions where I give you an outline so you guys have an easier time solving it and turning in that written homework. Again, the written homework is due in my office by 5 p.m. on Friday, not this Friday, but the following Friday, I think it's the 12th, and then every 2 weeks thereafter. So let's continue with this. We'll do some of these in class, some of these we will do as DQs, and some of these we will do here, and we will talk through, give you some outline. Okay, so let's talk about graphing transformations. In a pre-calc class, we learned, or college algebra class, you might have done this, we learned that certain transformations of the graph of a function can be achieved by a simple change in the formula of a function, adding a piece, subtracting a piece. Outside of the function, they move up, down. Inside a function, they move left, right. And basically, by setting the argument equal to 0, we'll determine whether they go left or right. We also have other shifts too. So let's talk about horizontal shifts first. So this is for a function on the reals. So from real numbers to real numbers. And we want to consider that a point on the graph, say C and f of C, those are a particular place. And if we want to shift it horizontally up or down, we add, or horizontally left, right. So on the horizon, we put it in for our x coordinate and we add it h units horizontally. C plus h, and then wherever f of c was, will stay there. If we do this for every point, we represent a transformed function as a new function. We'll label it g. FG, not because of anything special, which is also on the reals, and they have the ordered pair of x and g of x. We've basically shifted horizontally our function. Matching x coordinates, x would be equal to c plus h, or c would be equal to x minus h. Depends on how you look at it. Matching y coordinates, g of x would be equal to f of c, right? So they'll be equal to each other. Combining these last two statements, so notice that f of c, and we know that c is equal to x minus h, we end up with g of x is equal to f of x minus h. How do I explain this in a pre-calc class or college algebra if we're talking about this? Since the graph h units to the right, so if it's x minus h, it means h units to the right. So h greater than 0 means negative right, means to the left. So if h is less than 0, meaning it's a negative, then it's negative right, which means left. For a quadratic, the vertex is at h and 0. So there's horizontal shifts may seem backwards. I often explain this as if I take that x minus h and set that equal to 0 and solve, I will get that x is equal to some positive h, which means right. If this was x plus h, then it would mean some negative h, which would move it to the left. So I always say, put your argument, whatever's in your parentheses, equal to 0, solve it. That'll tell you whether you're going positive or negative. If it's negative, you're going left. If it's positive, you're going right. So oftentimes in a pre-calc class, that seems to work better. Again, when we think about a quadratic, you need a bigger x to get the same f of x value you got from the simple quadratic. So there's the initial quadratic, x and x squared. You'll see that when x is 0, you're at 0. but you need a bigger value to pull off the same thing. So because this next one is x minus 3, to get my first step, if I plug in x equals 1, then minus 3, 1 minus 3 is 2. That would give me the 4. 2 minus 3 is going to give me -1, so that's how I get to that. 3 is going to get me my vertex. So I need a bigger x to get the same value that I got before for my y value. Other transformations, if I start with the graph of f of x is equal to x squared, and I want to find a formula for g of x relative to each of the following. So I want to find a g of x that shifts upwards 3 units. So again, this time I'm not going left, right, but I want to go up, down. I would just add 3 outside, right? So it would be g of x is equal to x cubed or x squared plus 3. That's going to shift me up 3 units. Or if I wanted to go down 2, it would be -2. A vertical stretch by a factor of 2. So that's where, what do I want to do if I want a vertical stretch? If I want a horizontal stretch by a factor of 3/2, where do I put these? So let's talk about these a little bit. If I want a vertical stretch, where does that go? Oops, let me, well, let's apply these. Let's just go right in and apply these. So this says if f is going to be a function, I'm going to find a formula of the function whose graph is obtained from the graph of f by shifting 2 units to the left and then by stretching vertically by a factor of 3. So I'm going to make a vertical stretch by 3, but I'm going to do it after I shift it 2 units to the left. And then I'm going to find the function of the graph that's obtained from the graph of f by stretching vertically by a factor of 3 and shifting 2 units to the left. So we're going to do one going one way. We're going to go shift first 2 units left, then stretch vertically by a factor of 3. And then we're going to reverse the order and we're going to see what happens. Come on. Not happening. Where are we happening? There we go. Okay, so first we want to transform it 2 units to the left. So remember, if it's left, it's a negative right, however you want to think of it. So that would be +2. And then I want to stretch vertically. So I did a horizontal shift, and then I want a vertical stretch. The vertical stretch is by the factor of 3. That's happening outside. So 3 of my f of x plus 2. Remember that f of x is my map. So here I'm looking at it just in general. But say my map was, I don't know, x plus 2 or something, or no, not x plus 2 because that's what we're using. Let's say it was x squared. Okay, x squared. Then the transformation shifting it to the left is going to be, I'm going to put parentheses around my x and it's going to become x plus 3, the quantity of x plus 2 squared. And then the vertical, the stretching by the factor of 3 is applying in front of that. So it would be 3 times the quantity of x plus 2 squared. So it's where it goes, but because we don't know our map in this particular function, we don't know what that map is. We just know that f is a function. That means f of x is a function. Now I'm going to map that. And so that's what we did. This is very general. So my transform shifted would be f times the quantity of x plus 2. And then the stretching would be the 3 in front of that. Now going the second way, and I should note that this is a horizontal combined with a vertical. Okay. So then the next time it says do it in the other order. So apply the vertical stretching first. So that means 3 times f of x. Then we're going to apply the shifting 2 units to the left. So that's 3 times f of x plus 2 in parentheses. Okay, again, if you do a horizontal and a vertical, they don't matter. It doesn't matter which order you go in, you still end with the same result. This isn't always true. It is always true if you're doing a horizontal and a vertical, or a vertical and a horizontal. It will not be true if you're doing a, say, a horizontal shift and then a horizontal stretch. You have to apply those in the proper order. And we'll see that as we go through this. So that's part A. Part B, George and Laura are trying to graph 2 sine of 3x. Laura wants to do the horizontal compression followed by the vertical stretch. But George insists on the reverse order. Which one matters and why? Does it matter which order is correct? So let's apply both students. So Laura and George, we're going to apply what they're doing. We'll start with Laura because I think Laura was first. So the base function is y equals sine of x. So Laura says horizontal compression. So that first step is sine of 3x. Then the vertical, my face is in the way. Let me move this out of the way. Okay. Okay. Then the vertical stretch, which means we put the 2 in front. So we have 2 sine of 3x. George is doing the vertical first. So vertical says 2 of sine of x. Then the horizontal compression gives us 2 sine of 3x. Both work because g of f equals f of g for these function transformations. What that means is that they're you can't always do this. I guess what I'm trying to connect here is that this does work because they're different types of transformations. And transformations as a whole tend to be commutative, meaning you're totally fine. You guys who have taken linear, and some of you will have taken linear already, some of you may not have, or might be in a linear class, you're going to find that this is not true for everything. Beautiful thing about function composition is it does work this way, though function composition has the restriction that you can't do the same type of function with each other. And we should see that in the next one. There we go. All right, so John is moving. This is part C of the same question, and this is one of the homework questions. John wants to move up, and Teresa is willing to move to the left. Can they graph sine of x plus pi over 4 plus 1? So John's move up is that plus 1. Teresa's movement to the left is the negative pi fourths. Remember, it should be x minus h. So because it's a plus, that's a negative positive, a negative left, or negative right. What 2 graphing transformations would they use, and does the order of the transformation matter? So this is what John wants to do is move up. So that is a vertical shift, and a horizontal shift is what Teresa's doing. So the good news is they really don't matter. The order of these don't matter. Um, John's doing the vertical shift. Teresa's doing the horizontal shift. One's vertical, one's horizontal. Order's safe. Now, let's state a general principle about these transformations on the basis of part A, B, and C. And you can obviously use your own language on this as you do this. I used very basic language because I needed to fit it on my slide, so keep that in mind. But I tried to be very concise. These functions, horizontal and vertical transformations, are independent, so it does not matter if vertical or horizontal transformations are performed first. Again, I got tight because of here. I would have been a little bit more I would have explained this better if, or in more detail if I was writing this up for a piece of paper. But you guys can be more detailed in that, but this is in general what you're saying. There you go. Okay. Some notes about the NES. That's where I can, I'm going to include these. This is an average rate of change over. my y over change of my x's. That is an average rate of change. Okay. I should note that the difference quotient is a specific rate of change. So not an average over the whole function, but a very specific for particular locations. Interestingly enough, if I looked at particular locations for my average rate of change here, for this average rate of change, you will note that these create a slope. This is the slope formula. Because formulas are all made up. They don't really exist. They're really just making things easier when we talk about particular topics, not actually the deeper understanding, which is sad. This is the deeper understanding. Slope is an average rate of change between a particular set of points that you've chosen to use. A difference quotient is the same thing at a particular location. Again, we're talking about particular locations. And it should be noted, function composition can be written in either way. And there's even, as you guys explore textbooks, because you're going to use whatever textbooks your school that you're teaching at is providing or has agreed upon. And when you're high enough up at a particular location, I know people who I've taught that are actually deciding what textbooks will be used, along with the committees involved in those for Tolleson School District right now in the Southwest Valley. But some textbooks actually write f of g. Oops, go back for a second. Uh, Without the circle, the center circle there, and they just have a space. I don't like that notation. I'm not a big fan of it because I feel like if somebody is writing it and gets kind of lazy, it looks like F times G, which is a different type of action. It's not a function composition. It's a function product, and you can do those too. So I don't like that other notation, though it is possible that you will see it. I've taken an NES and involved with NES on the changing questions and stuff like that. I will use, and I'm adamant that they use one of these. I don't care which one. Either one of these are valid. I do not like the other notation because I feel like there's a chance that people will make mistakes. Here we have another function, another question from the homework. Suppose that x-intercepts, so we're talking about x-intercepts of the graph, are at 4 and 7. Okay. Now that's not 4 comma 7, that point. That is at x equals 4, it crosses the x-intercept, and at x equals 7, it crosses the x-intercept. So then the question says, can you find the x-intercepts of the graphs of the following functions where the change is in there? And if it's possible, tell what they are and how you got there, explaining why. If they're not, tell me why also. So again, you should be trying these on your own before you kind of look at these parts of the videos, for your benefit. The reality is I can give you all the answers, but that does nothing to prepare you to take the test, because you have to be able to get the answers in a testing environment where you're locked in a particular area and all you have is a small paper whiteboard and a dry erase marker to work with. Um, and they're really kind of crappy whiteboards, to be honest. But that's all you have. You don't have anything with you. You've been checked. You didn't bring anything with you. You're in there for 5 hours trying to do this. So please understand that you have to know how to do all these on your own. So f of x minus 3 is a shift to the right of 3. Well, that one's pretty easy. If I'm shifting 4 to the right and I'm shifting 7 to the right, I hope I did this in pieces. We're going to find out, or if I just put them all in. Dang, I did. Okay, well, that's fine. Um, so the easy way is consider replacing the x with 4 and then with 7. So when you replace the 4, you would go 4 plus 3, which would be, again, you're solving for x. So you're solving at 4x. you're going to get that 4 is equal to 7 and 7 is equal to 10. So you would replace your x-intercept of 4 with 7 and your x-intercept of 7 with 10. You shifted it to the right 3 in each case. The other one, so the next one, 2 times the function of 7x plus 1. So you have quite a few things happening here. So we need to first consider what each piece is doing. So that function has a vertical stretch by 2, a horizontal stretch by 7, and a horizontal shift by 1. Okay, so first, the vertical stretching will not change your 0. So it doesn't change an x-intercept. It is a vertical stretching. Where it was is still there. It's pulling the top and bottom to be steeper. So that won't change anything. The horizontal stretching will, but so will the horizontal shift. So we say, okay, let's replace our x in 7x plus 1 with the 4. So we set it equal to 0 again. So then when we solve this, we would have that x is equal to 3/7. And then when we do it with 7, we would have that x is equal to 6/7. So again, the vertical stretching doesn't change anything, but both the horizontal and the horizontal stretch and the horizontal shift do. So setting that equal to 0 and going through the process. And you may look at it like, so a way you guys might see this as 7x plus 1 equals 4, and then solve for x, meaning you would minus 1 from both sides. That would give you 3. Then you would divide by the 7, which would give you 3/7. Okay. And then do the same thing with the 7, setting it equal to that and solving. Because you know that f of 7x plus 1 is equal to 0. So we just replace that to make that shift. The next one, 7 of f of x plus 1. Now, this is a vertical stretching by 7. It won't affect the y values at 0, but the vertical shift up 1 unit will affect the y value. Okay, that's outside the actual argument. That means it's going to shift it up. So you were at 4. I can tell you that that function at, not at 0, not at the x-intercept, but at x equals 1 is 4 and 7. But I can't tell you how that shift affected the other side. I don't know the function. In each of these cases, I don't actually know the map. I just know how the map is affected. And by map, I mean the equation that maps where x goes. I don't know the equation that maps where x goes. And because of that, I can talk about where the intercepts are on the other two, A and B. I can absolutely do that. I don't need to know the equation. And a lot of you think, well, you have to have the equation to do stuff. You do not. I know what to expect based on how the function's written. That's all I need to worry about. So knowing where my zeros are is essential depending upon what I do to an equation. In the real world, right? When people are using mathematics in the real world, it's not necessarily about an equation. It's about what do you expect to happen? And if you can say something about what's going to happen, no matter what the equation is, that's pretty powerful. And that's the beauty of mathematics. So there we have that it's impossible to tell with the information given because that shift up, we don't know how that affects it. We don't know if it moves 4 to the left, that x-intercept from 4 to the left, or if it moves it to the right. We don't have any information to tell that. And so we cannot without the map or the equation. All right, images and inverse images. So if we have the function a to b, and we have an element of A that maps to B. We can consider that f of A is called the image of A under F. So the image of whatever our x is under our function. It's like asking, what does A look like now after we do this operation? After we do this procedure, what does A look like? If S is a subset of A, we define that to be f of S such that S is an element of our subset. The set f of S is a subset of the codomain and is called the image of S under F. There's a lot to do to build range, actually. So thinking forward from A to B. So these are the two different interpretations. One is to evaluate it. We can evaluate our function at every S in the subset, collecting all of the images into a set. Thinking backwards from B to A, this is like a test condition. We can take a look at f of S as a test condition on the elements of the codomain. So we can take a codomain element and say, does this give us an input? And if it does, then we get that. That's easier to work as a test, not as we're testing a particular result. We're not testing all results. That thinking forward works for thinking of all results. So there's different ways to look at it. So if we're given the B, we then check it and find out that there exists exactly one element in our S such that f of S goes to B. Again, if there's two elements that go there, we're in trouble. So interpretations matter. Here we have an example. So this is on the reals, and our function is the square root of x minus 3. And we look at it as a subset of 0, 1, and 2. And we can compute the set f of s. Which of the two interpretations for f of s are we using when we do that? Are we using it as a test? Are we using it from B to A, or are we using from A to B? Okay. Oops, wait. I don't want to, that one. Oops, wrong way. Hold on. That ended. Stop it. Let me go back. Nope, wrong way. Okay, go back. There we go. In this case, because there's only 3 inputs, we're just going to plug those 3 in, right? We're going to say, okay, does it exist? If I plug in 0 here, this doesn't exist, right? That's square root of a negative number? Nope, not a real number. If I plug in 1, not a real number. If I plug in 2, not a real number. So on that subset, nope. It's nice and easy. Now, let's say we look at our outputs. We want to try our outputs. There we go. Okay. So we're going to let S be closed interval from 1 to 9. And then the question is B4 an element? In this case, we're using it a test. We're using it as a test. We're plugging in 4. We're saying, okay, can I get 4 out of this? Well, can we get 4? Remember, B being an element of our result, meaning could I somehow plug in from 1 to 9 and get 4? So this is a test. In this case, we're using it as a test. Can I get to 4? Well, if I look at what I would need to have to get 4, what number would that need to be? It'd need to be the square root of 16, which means I would need to have something minus 3 that gave me 16, which would be 19. 19 minus 3 would be 16, and 16, the square root of 16 is 4. Okay? So no, 4 is not an element. And we can test these. So again, there's different ways. Some applications to geometry in this case. One use of functions is to change the shape of objects. You can examine what an image looks like compared to the original shape. You will almost always end up with a mirrored thing from an image. So if we consider the function of the cross product of reals to the real, we can define that as f of x of y is equal to some x. Okay. Um, and we can consider that. We input point xy in the plane, and then it spits out a particular value where we're really looking at the x coordinate of that point. That's very useful. Let's talk about range. The image of the domain of f of a is called the range. So this is everything that comes out. So this is the subset of our initial set of B that actually is output, or the image of. Thinking forward from A to B, this is the collection. So we obtain the range by evaluating f at every possible A in our set A and collecting all of those f of A's into a set. That's range. All of the possible B's are our codomains, so they're different. Thinking backward, test condition. So we're thinking backward from B to A. In this case, we're given a particular B. We check it. B is in the range exactly when there exists an element in A, where f of A gives us B. So that's how we work backwards. Which one should you use? Both. Use whichever one is right for the question that's being asked. If you're given a result and they want to know if that could be a possible, if there could be a possible input to give that, you're using it at like a test condition. If I'm given a birth date and I want to tell if one of my students have it, I would have to take a look at that birth date and then test back, is there a student that matches it? If I'm going the other way, I'm taking every one of my students and calculating their birth dates. And then that's my range. Inverse images. So we're going to get real wild with this, and then we're going to apply it to something that doesn't have numbers. So this is going to be fun. And you're going to get to explain it. So f of A to B pushes forward a subset of A to subsets of B. To pull back subsets of B to subsets of A, so for T, a subset of B, we define the inverse of T, so f to the power of -1. That -1 is not applied to a number, that is applied to a function. So it's different than something being raised to a -1 power. We use that notation. It's probably not the best notation. So f inverse of T, we would be the set of A's such that f of A is an element of T. F inverse of T subset of A is called the inverse image of T under F, or the pre-image of T under F. Here, F inverse is referring to the running the map backwards from B to A instead of from A to B. A better way, ooh, it's not showing up. Okay. F inverse is not a function or a relation, just a subset of A. Oh, okay, I was done. Oh, no, I wasn't. Oh, dang it. Okay. Here's an analogy. An alcoholic is addicted to alcohol. A shopaholic is not addicted to shopahol. But we get it. They have a self-destructive compulsive behavior in a similar way. So x to the power of -1 is 1 over x. F inverse is not 1 over f. That is not what it means. It is the opposite in a way, though backwards rather than upside down. So that reversed f is more accurately what we're talking about when we talk about inverses. Though in the original typesets of books and stuff, that was more difficult to do. Yes, I have one in here. No, that is not a typeset. I actually pictured and flipped a regular F. It's more difficult to do, even with technology. So we're not going to see it noted like that. though that is more accurately what's happening when we talk about inverses of functions. We just want to be clear that these two are not the same, x to the power of -1 and f as a function notation to the power of -1. If I was just using f as a variable, f to the power of -1 is 1 over f. So we have to be clear contextualizing what's actually happening. And that can be bad with some textbooks as you read them. You will find that. So two interpretations, thinking forward from A to B. This is of the inverse idea. A to B is a test condition now. Before it was B to A was a test condition. Now A to B is a test condition because we're talking about the inverses. To find f inverse of t, we check each element of A and compute whether f of A goes back to an element of t. If it is, it's included in our f inverse of t. Thinking backwards from B to A, this is a collection. So now we're taking every result and collecting all of our A's, if you will. So our f inverse of t, we run through each element of t and compute whether there is an f of A equal to it. The inverse image of t, the set t, this collection of all elements obtained this way is exactly f inverse of capital T. I'm making these distinctions because you'll see in the question. This could be the union. This would be the union of all t's in T, in capital T. And that big U, the big cup, is what we use to denote all unions. So just a collection of the unions. Mathematical notation gets more challenging as you go higher. So it's nice when you can figure out what that notation is, but oftentimes you'll have to read the context to understand. So here's the problem that you guys have. Some of them, like I said, oops, nope, don't go there. Go back. Okay. Some of them I give you guys the question. Some of them I do as outlines. This one, just going to talk through some words. So A is a set of all humans. B is a set of all human males. So the definition is we're going to define our function to be from A, all humans, to B by the rule that f of A equals A's biological father. So this means for each human, each human has a biological father. Very simple, very straightforward. So in words, you're going to describe the range of that function. So is this all human males? For my males in the class, consider whether you have children. You are in set B, but are you in the range? So be careful with your wording. And I may put this as a DQ. I might have this as a DQ so you guys can talk through this. Because I feel like mathematics, the idea that mathematics is done in solitude is so wrong. And historically, we see that doesn't work. So I think you guys should talk this over. If Y is an element of B, so Y is a human male, then in words, what is the set of the inverse of the set Y, subset of Y? And then consider what that means, and then do the same with if X is an element of A. In words, what is the inverse of the set of X's? Remember, X is an element in A, so that means X is any human. You pick the human. Actually, don't. Your audience always picks the human, so whatever they decide. What does that mean? Well, we know that f of x goes to their father. So for each of you, it's talking about your individual father. For me, it's talking about mine, my biological father, right? That's what we're talking about. So everybody has that. And so then what is the inverse of that? And again, I'm not going to give answers on this. I want you guys to think about this. You're writing it up in your own words. We might discuss this in class day one or the first day we actually meet just for fun because it'll be due the end of that week by Friday. So, but my hope is you already started to come up with something. If Y is an element of B, then what is the inverse of Y? So again, we're taking what we found in B and we're applying the function to it. So in this case, your answer should depend on whether Y is in the range, because we're saying any Y in B, that means we're talking about me who has children and one of you male students who may not have children. So we're talking about both. So then the question becomes, well, okay, which one of us is in the range and how does that apply? Okay. Um, Let's continue this a little bit farther. We're going to talk about injective, surjective, and bijective. Again, I've given you quite a few answers to some of these as we've moved along, but not every one of them. How many A for a B? So what makes a function from A to B? A function is given any A, there exists exactly one element in B such that f of A equals B. That's a function, right? That was important. That's how we passed the vertical line test. Okay. Another question, though, given any B in our set B, how many elements of A go to B? Again, I could have a quadratic from x equal to -2 and it's squared, that would be 4, but also x equals 2 would go there. So while each x has exactly one B, and we're okay with that, it can be the same B as another. That works, and it's still a function, but no A gives me two different results, right? So -2 gives me 4, but I don't have that -2 gives me 4 or -4. It's only 4 in the quadratic. So again, each input gives me only one output. This next question is, well, given a B, say 4, how many elements in A go to B? Well, -2 and 2 both go to 4. So that becomes a little bit different. So given any B in B, how many elements are in the set F inverse of B? And this might help make the previous question make sense, which is why I want to go through this. Just knowing F is a function doesn't give us that answer. We don't always know that because we don't know necessarily what the function is. So some specific questions. For every B in B, does F inverse of B have at least one element? Remember, B is a codomain, so not every B is necessarily an F of A for some A. So if it has at least one, that's has some power. If it has at most one element, so if it has at least one, then it becomes one thing. If it has at most one, it becomes something better. So if there's a bullet hole in a wall, the ideal scenario is that there's one possible weapon fired from one possible location that could have put the hole there, right? In our CSI type thing, we're expecting one. And so that's what we're trying to figure out. We have the hole. We want to figure out exactly the bullet and where it was fired from. That's what the at least and at most will help us do. These lead to defining properties of functions. Injective. So, dang it, I am like bad spot each time I move my face. All right, here we go. All right, we say that a function f of A to B is injective if any of these equivalent properties hold. Not all of them, any one of them. If you prove one of them, you've proved injectivity. One, given any A1 and A2 in A where they're not equal to each other, so 2 and 3 not equal to each other. If they're not equal to each other, then f of 2 can't equal f of 3. Okay, so if that is true, then it's injective. Given any A1, A2 in A, again, f of 2 equal to f of 3, if that is true, then 2 equals 3. All right, then it's injective. So this is where you could look at 2 and negative 2 in a quadratic. A quadratic is an injective, so it works. If I say f of negative 2, that's equal to 4. If I say f of 2, that's equal to 4. Then it says here, then negative 2 equals 2, which isn't true. So it would fail that injective property. Given any element in B such that F inverse of B contains at most one element, meaning there's only one output that matches each input, well, then you get injectivity. Injective is also called one-to-one, a one-to-one function or injection. And we're going to do the same. Here's an example. So is this function injective? The name of Arizonans to birth dates of Arizonans. This function is the canonical map from each person's name to their birthday. No one was born on 2 days. Everyone has one date as their birthday. This is a function. If a function on the reals is increasing or decreasing, it's injective. So if we can show that a function is increasing or decreasing, we can show that it's a function. Conversely, suppose that f is injective. Is it necessary that f be either an increasing function or a decreasing function? So I'll let you think about that. If we've proven it's injective, does it necessarily mean that it must be increasing or decreasing? And yeah, at least on the where we're looking at it for sure. Surjective. This is, again, the same idea. We're going to have these equivalent properties. If any of these are true, it's surjective. So if I have a B in my set B, there exists at least one A such that f of A equals B. So that means everything in my codomain must be in my range. That's pretty powerful, and that's hard to prove. So that one's tougher. F of A is equal to B. This is, in words, the range of F equals the codomain of F. Again, challenging to prove. It's easier to look at this as a test condition, but it's hard to prove surjectivity. This is one of the ways you can do it, and it's given any B in our capital B, any element of our capital B. We take the inverse of our set of elements, and it contains at least one element. That actually is easier to prove usually. Usually it's 1 or 3 are the two easy ones. Surjective is also called onto or surjection. Bijective. If you have injection and surjection, you have bijection. So if you have one-to-one and onto, you have bijection. So that's the big rule here. You need to prove both properties if you're trying to prove bijection. I will say mapping is interesting. If you wanted to choose bijection, show bijection, and you have a map, you have this drawn out graphically, you know what the equation of your function is. An interesting property holds. If you think about those, the injection and the surjection, it means that not only will it pass the vertical line test for a function, it'll pass the horizontal line test, meaning horizontally, it'll only hit the graph of our function once. And if it does, then you have a bijection. It has to pass both of those. So on a map, it's often easier to tell, though those proofs are not considered real proofs of a function. So be careful. If I look at f of x equal to x, this is the standard horizontal line. For you guys, I guess it's that way. That one is only going to hit this way once. It's only going to hit this way once, vertically once, and horizontally once. Therefore, it is a bijection. Um, the square root, I'm going to skip because we're all good that the quadratic you would hit twice. It's a U, meaning I'd hit it twice, which means it's not a bijunction. The next one, we have to look at where it exists. That's the standard kind of come up and go, right? Or for you guys, right? Come up and go. Do that over here. There we go, like that. That one is where it exists. It doesn't actually, it always keeps going up, even though it's slower. So it will only hit once that way, and it'll only hit once this way. So where that exists, it is a bijection. The problem is this is showing it as mapped from the reals, all reals, to all reals, in which case, no, this is restricted. With restrictions, that one totally works, but without restrictions, that won't work. Okay. Um, let's see. Move it again. Okay. All right. So this is on the reals. Given this function, x squared times the quantity of x minus 3, given a real number b, find the number of elements in the inverse of the set b, and the answer is going to depend on b. So you may want to draw a rough graph of this function. You'll probably need ideas from calculus to complete this exercise. You may want to distribute that x squared through and look at what this cubic function is, and maybe find intervals, well, and then maybe look at where those particular values are and where it's increasing, decreasing. You can, again, calculus will help with this. So you can see where you have one element, because some places on some intervals you have only one element. On some intervals, a couple, you only have two, and then on others you have three. So please look at these intervals. Find the three intervals whose union of R such that f is injective as a function on each interval. So again, you're going to group it into intervals and then use the answers from A and B to define the domain and codomain of the three bijective functions. You're actually coming up with three new functions to replace f to map it where it's bijective. And if you do A and B, well, it should make that easier. This one, if you have questions on Monday, our first class, I have no problem going over it. Yep, that is where we will stop for this video. And then we'll go through the lecture on, I'll answer questions as you guys start this. My hope is you've already watched all these videos and you're prepared. You've already started this written homework. You've done your ALEKS, both your ALEKS initial knowledge check and your ALEKS first test prep, which is due this week. Next week, when we meet and talk about this, if you have questions on this, I'll gladly answer them. Otherwise, you guys will be wherever you're at. You'll continue with this homework, finish it off, and turn it in not this Friday, but next Friday. All right, you guys, have a good day.